Okay, so here we are in our last chapter, chapter 11. We're going to be taking a look at the beginning of chapter 11, we have to start by reviewing some concepts that you've already learned in pertaining to functions, and we're going to build upon two new concepts regarding functions. But first of all, let's review what we already know in terms of functions. Recall, we may have different types of functions. We've seen all different types. Let's say f of x was a negative 5x plus 3. Remember, we considered this a linear function. We may have the function g of x. That could equal to, let's say, x squared minus 2x plus 1. And we would consider this a quadratic function. If we had a different function, let's say, h of x, that might equal, let's say, the square root of x plus 4. And this, of course, would be a radical function. And lastly, maybe we might have the function j of x. And the function j of x could equal to, let's say, 5 over x minus 6. And this we considered a rational function. Those are the types of functions that we have seen so far. We can classify them depending upon what type of function that we have. Remember, in all of these cases, x was considered the domain. That was the input, your x values. Whether you have f of x, g of x, h of x, j of x, that didn't make a difference. Your f of x is your range. That's the output values, okay? And a few things that we have done with functions so far. Recall, one of the major things that we did was to evaluate your function. And recall, for that, not only do I have to give you the rule, but I have to give you a specific value of x to plug in. For example, I could ask you to evaluate maybe f of 2. I could ask you to evaluate g of negative 3. I might say evaluate the function h when the input is the number 5. Or I could even say evaluate the function j when your input domain is 0. And recall, when we evaluate a function, what you have to do is you have to take your input values, what's inside the parenthesis, and you're going to substitute it for your variable x. So for the first one, f of 2, that of course means we would need to take negative 5 times the 2 and add 3. And when we were to simplify that, you would get a negative 7. And remember, we can write it as the ordered pair, 2, negative 7. When we want to evaluate the function g, we would now have to substitute in the numerical value of negative 3, in which case we would have negative 3 squared minus 2 times the negative 3 plus 1. And when we use the order of operations to simplify that, you would of course get the number 16. So the ordered pair, of course, would be negative 3, 16. If we want to evaluate the function h when your domain input is 5, of course now we're going to go with the square root of 5 plus 4, and when we simplify that, we get the number 3. And so our ordered pair would read 5, 3. And lastly, let's go and evaluate the function j when the x value is 0. And in doing so, remember, we would plug 0 in. And once again, when you simplify, you get a negative 5/6. So our ordered pair would read 0, negative 5/6. And that's just one major thing that we have done so far with functions. We evaluated them at a particular x value. You may recall other things that we did pertaining to functions. We talked about identifying the domain, of course. in which case, remember, we are looking to see, are there any restrictions on the values of x that could be? And remember, when we were talking about all the polynomials, in this particular case, f of x and g of x, when it comes to f of x and g of x, because these are in fact polynomial functions, linear, quadratic, we had said that the domain was all reals, that it can go from a negative infinity to infinity. Okay? When it comes to, let's say, the function h of x, we dealt exclusively with square root functions back in chapter 9. And when we talked about the domain of square root functions, we talked about how the radicand must be a positive quantity. So in this particular case, the x plus 4 from our function h of x up above, we stipulated that it had to be greater than or equal to 0, because that would indicate that it is a positive quantity. And when furthermore we went and solved for x by subtracting the 4 over, we got x had to be greater than or equal to negative 4. Remember, we wrote it as the interval notation from negative 4 to infinity. And then for the last one, j of x. J of x we dealt with, not so much from a graphic point of view, but it came in handy when we were solving these rational equations, because once again, our denominator could not equal 0. So when we look at the function j of x up above, we would be able to stipulate that x minus 6, the denominator, could not equal 0, because that would give us something that is mathematically undefined when we talk about the real number system with functions. And of course, to solve now for x for the j of x function, we would get that x could not equal to the number 6. And that's what we have done so far in terms of functions. We began this in right before our very first test. We talked about function notations, we talked about evaluating, and we talked about identifying the domain. And each time we introduced some new functions, we reviewed this idea of evaluating and its domain. But there are two other concepts involving functions that we have to address in section 11.1. And the first idea is what we call the composition of functions, or composite functions. So we have the composition of functions. Sometimes it's also called composite functions. And basically, what you're going to be dealing with here is more than one function, multiple functions. Okay? Pretty much you're going to have a function within a function. So you're going to have a function within a function. Okay, and right here is the abbreviation for within. And this is the notation that we use for composite functions. And depending upon the book that you use or the professor that you may have, they might use a slightly different notation. Sometimes it may look like this: f of g of x. Other times they use a lot more parentheses, and they might write f of g of x. Other notation that is sometimes used: f of g of x. And I actually prefer this last one here because it makes the most sense in terms of the fact that you have one function within another function. Or if we want to write, we could say the output of the inner function becomes the input of the outer function. Because remember, when we deal with functions, it's all about input and output. When you substitute something in, you get something out. And that's why the output of your inner function, so in this particular case, if I was to use this last way of writing, the output of g of x becomes the input of the function f of x, because that's the outer one. And let's see how we're going to use this function, composite functions. Let's come up with an example. We'll just start with something simple. Let's say the function f of x might equal 3x plus 1. And g of x might equal, let's say, negative 2x minus 5. So here we have two functions on how they are defined. The function f of x tells us to take the input x, multiply it by 3, and add 1. The second function, g of x, is going to tell us to take the input x, multiply it by the negative 2, and then subtract 5. So from a composite function type problem, I could ask you to, let's say, evaluate maybe f of g of, let's say, the number 1. Okay, so we want to evaluate the function f of the function g when your input is 1. So the first thing that we're going to have to do is evaluate the function g when the domain is 1. Don't even think about the function f right now. So let's take a look and evaluate the function g like we did up above. And according to the function g, I must take my input, multiply it by the negative 2, and then subtract 5. So in this particular case, we would have to take negative 2 times the input, which is 1, and then I'm going to subtract 5. And we now want to simplify this. And if we do so, negative 2 times 1 would give us a negative 2, minus 5 would give us a negative 7. So that negative 7 is the output when we put in the input of 1. So that was the output of the function g. Now it's that output that occurs inside these brackets, so that is going to now become the input of the function f. And so what does f tell us to do? F tells us to take the input, multiply it by 3, and then add 1. So we're going to do 3 times the negative 7 plus 1 more. And now we would once again use the order of operations to simplify this. And in doing so, you would get a negative 20. And that would be your answer to this particular composite function. Okay? So once again, you start with the innermost function, and you plug in your value of x into the function rule. Whatever number you get out then becomes the input for the outer function, in this particular case, f. Let me use the same two functions, okay, which we have up here, except now I'm going to just change things around a little bit. Let's say I want to evaluate maybe g of f of negative 3. Now once again, I'm going to start with the innermost function. And for the innermost function, which is now f, I have to evaluate the function f when my input is the negative 3. So I'm not going to worry about the function g right now. And I'm going to evaluate the function f. And according to what we have up here, f tells me to take the input times the 3 and add the 1. So let me write that down. And now I want to evaluate this. I want to use my order of operations to simplify what I can inside the brackets. And in doing so, we would get a negative 8. That negative 8 is the output of the function f. And that will now in turn become the input of the function g. So what does g tell me to do? But take -2 times the input, and then we have to subtract 5. And in doing so, that would give us the number 11. So that would be your solution. Okay? Let's try another one. Let's change up the functions a little bit. Let's say the function f of x is defined by 3x plus 2. That's 3 times the input plus 2 more. Let's say we have the function g of x. That is going to be the input squared minus 2. Well, let's see what we can do now. Let's say I'm going to ask you to evaluate maybe f of g of 3. Once again, let's work through this one together. In which case now, I'm going to ignore the function f for the moment, and I'm going to evaluate the inner function g when the input is 3. So that would give us a 3 squared minus 2. And when we simplify that, we get 7. So that's 7 now. Once again, that's the output of the function g, which will now become the input for the function f. And according to the function f, I need to do 3 times the input and then plus 2. And when we do that and simplify, we get 23 as our answer. Let me give you one to try on your own. Same 2 functions, f of x, 3x plus 2, g of x, x squared minus 2. What if I want you to now evaluate, let's say, the composite function g of f of -2. Take a moment, pause the video, give this one a try, and when you come up with your solution, turn the video back on and let's see if you get the correct answer. Well, if we were to evaluate this, we're going to start with evaluating the function f. And according to the function f, I have to do 3 times my input, -2, plus 2 more. And when we simplify this, that in fact would give us a -4. And so now, that -4 is the output of f, which will now become the input for the function g. Once again, what does g ask us to do? We have to take the input, which is the -4. I'm going to square it and then subtract 2. And when we simplify what we can, we get the numerical solution 14. And hopefully you did too when you tried it on your own. Okay? So that's one major concept that's new here in section 11.1 involving functions. The other concept that we have to talk about in section 11.1 is the concept of what we call the inverse function. And the notation that we use for the inverse function looks something like this. It's f to the -1 power of x. That's the notation that mathematicians use to represent an inverse function. Now, remember when we first talked about functions way back at the beginning of the semester, we talked about how a function is a special relation. Okay, so that's a special set of ordered pairs. So let's say f of x, the function, is equal to our set of ordered pairs, let's say -1, 3. Let's say then we have 2, 5, and maybe let's say 7, 11. That's the function being represented by this set of ordered pairs. Well, if I was to ask you for the inverse function, okay, it's simple enough. The inverse function would look something like this. 3, -1. 5, 2. 11, 7. This set of ordered pairs, the original set, is the actual function. The inverse function also has a set of ordered pairs, but what do you notice about them? Well, for every x and y that we had in the function, when it comes to the inverse function, all you have to do is switch your ordered pair numbers. So it would now become yx. Okay, and that's what's going to be true about your inverse functions, that your x values of -1, 2, and 7 will now in turn become the y values, -1, 2, and 7. The y values of 3, 5, and 7 in turn become the x values of your inverse function, 3, 5, 11. So basically you have to switch your x and your y values. That's how you're going to get your inverse function if you happen to have a function defined as a set of ordered pairs. But what if we don't have our function defined as a set of ordered pairs? What if, for example, our function is defined by maybe f of x equaling to, let's say, I don't know, 4x - 7. We want to be able to find the inverse function, also written as an algebraic expression. And what I'm going to do is I'm going to give you 4 steps to follow to find the inverse of a function. So to find the inverse of a function, you're going to follow these simple 4 steps. Step 1, you want to replace f of x with y. So that function notation of f of x, g of x, j of x, k of x doesn't make a difference. Whatever that function notation is, we're going to replace it with a singular variable y. Step 2, you want to switch your x and y variables. Okay? Step 3, you are now going to solve for the variable y. You're going to use your algebraic skills, all of them, and you're going to look to get y by itself. And then, of course, finally, the new y equals, the new y equals your inverse function. Okay? So let's see how we're going to do that. So let's go back to the original problem that we had here, that f of x equals to a 4x - 7. And we want to find the inverse. So what do we have to do? We're going to replace f of x, okay, we're going to replace this f of x with the variable y. So y is going to equal a 4x - 7. Okay? Step 2, we want to take the variables x and y and we want to switch them around. So wherever we see a y, we're going to put x, and wherever I see an x, I'm going to put a y. In which case now I'm going to have x equals a 4y - 7. So now that I have switched x and y, my goal is to get y by itself. And this goes back to what we did, I believe it was our very first class together, where we talked about solving those literal equations, solving for formulas. In which case what we would have to do is start off by adding the 7 over. So that would give us a 4y equals x plus 7. And so now what would we have to do is we would want to divide both sides by 4, in which case y equals x plus 7 divided by 4. Now that we have isolated and found the new y, it is this new y that represents our inverse function. So we would be able to write that the inverse function is equal to x plus 7 divided by 4. That would be your inverse function. Let's do another one. For example, let's say f of x is equal to an x squared minus 1. Once again, we want to find the inverse function, and we will use our same 4 steps. So, step 1, we need to replace the f of x with the singular variable y. So now we're going to write y equals x squared minus 1. Step 2, we want to switch those variables x and y. So now our equation, when we switch the variables, will now become x equals y squared minus 1. And now, step 3, solve for y. We want to get the variable y by itself. I would begin by adding the 1 over, in which case now we would have y squared equals x plus 1. But we don't want y squared, we want just y. And we know to eliminate a squared quantity, what you would have to do is take the square root of both sides. In which case now, we would have y equals the square root of x plus 1. Now that we've isolated this new y all by itself, we would be able to write that our inverse function is simply now the square root of x plus 1 as our solution. So given the function, we're able to come up with the inverse function. Let me just show you one more. For example, let's say g of x equals x minus 1 over x plus 2. Now, once again, we want to find the inverse function. So let's start with our 4 steps. And this one's going to be a little bit more involved here. So, first of all, we're going to replace the g of x, that function notation, with a much easier variable y. And so now we move on to step 2. Step 2 tells us to take your variables, x and y, and switch them. And so now our equation would read x equals y minus 1 over y plus 2. Because we had 2 x's, we have to make them now 2 y's. We had 1 y, that becomes the 1x. Okay, that's how we switch them around. And so now let's take a look what we have going on here. This, you may recall, from way back in chapter, I believe it was 8, we called this a proportion because we had one ratio, one fraction, equal to another ratio, another fraction. And when we solve proportions, what we need to do was cross multiply. So I'm going to take the x in the numerator and multiply it with the y plus 2 in the denominator, and that of course would equal the y minus 1 in the numerator times the 1 in the denominator. Because remember now we're trying to solve for y because we're up to step 3. To solve for y, let's take a look now. On my left side, I'm going to have to distribute my x, and on the right side I will of course distribute the 1. And that would give us xy plus 2x equals y minus 1. Now remember, our goal is to solve for y. Now the dilemma here is that we have a y, variable y, on both sides of the equation. So what we're going to have to do is get anything with a y variable on one side. Anything without a y variable, we will move over to the other. In which case, I am going to subtract the 2x on both sides, as well as I will subtract y on both sides. And so now, let's see. Here, on the left side, when I combine what I can, we will be left with xy minus y equals, on the right side, I will have a negative 2x minus 1. Now remember, we're still trying to ultimately solve for the variable y. That's our goal here. Now on my left side, I have two y's. In order for us to get the y by itself out of these two terms, we're going to have to do a little thing called, of course, factoring. And so I'm going to have to factor out the common factor of y out of these two terms. And if I factor out a y from the first term, we're left with just x. And if I factor out a y from the second term, we would be left with a minus 1. So now on the left side, I have y times x minus 1 equals the negative 2x minus 1. And so now for our very last step, to get the y by itself, since it's being multiplied with the x minus 1, we're going to have to divide both sides by x minus 1. And in doing so now, we can simplify, and we would have that y equals the negative 2x minus 1 divided by x minus 1. Can't simplify anything. This is the new y, so that means the new y will in fact become our inverse function g of x, the negative 2x minus 1 over x minus 1. That's our new inverse function there. Okay. That completes section 11.1. Okay. For our next video, you will see that we're going to start learning a few other new types of functions. Okay. We're going to introduce exponential functions, and then we're going to talk about logarithmic functions. But that's to come. Okay. Be well.